Hello, this is ME490 Sustainable Energy Applications. My name is Abdallah Ghazali and I'll be giving a presentation on how to relate XCH4, SH2, and SCO versus delta, where XCH4 is the conversion of methane, SH2 is the selectivity of hydrogen, and SCO is the selectivity of carbon monoxide versus delta. Delta is this non-stoichiometry, which we're going to talk about in a moment. For the agenda, I'll provide some background information, then give an overview of the methodology, and then finally share my results. So, for the background, the big idea here is the solar chemical looping reforming. The reason why it's called that is because we supply solar energy to produce synthesis gas, which is a mixture of carbon monoxide and hydrogen right there. And the reason why it's a loop, it's called looping because we are basically continuously supplying Curie oxide throughout the cycle and reusing it, and during the reaction it's getting reduced and then getting oxidized, and it keeps doing that over and over and over. So let's understand how it works. So here we have a reduction reactor. We supply some methane, and once the methane enters, we also feed in some Curie oxide. So oxygen from the Curie oxide gets lost and reacts with CH4 to form carbon monoxide and hydrogen. With just the right amount of oxygen, we get this combination of products. However, with lower or higher amounts of oxygen from here, we can get different products, or actually this product along with other products, which we're going to talk about later. But for now, this is the big picture. So this Curie oxide, the oxygen gets lost, some of it gets lost, and so it comes out of the reactor with negative, with some lost amount. We refer to this lost amount as delta, and this is what we call the non-stoichiometry. It's the amount of oxygen that is lost relative to the Curie oxide right here. So we need to put the Curie oxide back to its original state by oxidizing it back, and in order to achieve the oxidation, we want a product that has oxygen in it. So we choose to put CO2 in. So the oxygen, some oxygen from the CO2 is going to react with this and get it back to CeO2 by giving it some oxygen. And because this has lost some oxygen, it's going to go out as carbon monoxide. It's not the only product that we can use. We can use water, so H2O. Oxygen from the water is going to get lost to CeO2, going to get it back to CeO2. And it's going to go out as hydrogen because it has lost that oxygen. We can put air, we can put anything that has oxygen in it in order to achieve the oxidation that we're looking for. So we're talking here about three quantities versus delta, the non-stoichiometry. So let's dig into it. So the first quantity is XCH4, the methane conversion. The second is, as we said, the hydrogen selectivity, and the third is the carbon monoxide selectivity. So those R's are basically flow rates. They're in units of milliliters per minute per grams of Curie oxide. So here we read this as the flow rate of methane in minus the flow rate of methane out over the flow rate of methane in. Here, the flow rate of hydrogen out over 2 times the methane conversion times the flow rate of methane in. And we get the idea. So the only thing that's given to us here is the flow rate of methane coming in, which is about 10 milliliters per minute times gram. But we don't know the rest. So how we're going to get the rest is we're going to use the lovely plot given by Professor Krinsky that shows the flow rates versus time. So we're going to use MATLAB code to extract some of this, to extract all these data points for each of the individual curves as vectors, and then those are going to represent the instantaneous flow rates. So if we plug those in, we get the instantaneous quantities of those. So we're going to get instantaneous conversion of methane, we're going to get instantaneous selectivity of hydrogen, we're going to get instantaneous carbon monoxide selectivity. But we don't want that. We want the cumulative, which we're going to talk about next. So here's the difference between instantaneous and cumulative. Instantaneous is at an instant in time, what's the value, versus cumulative is over this whole period of time, what is the value, or like what are the values. So the function that does that in MATLAB is simply called the cumulative trapezoidal function. It integrates cumulatively using trapezoids over the region that we're interested at. So if we want to find the cumulative flow rate coming in, it's COMTRAP-Z. We put the time that we're interested at, and we put the quantity that we are interested in inside the argument, and we get out, what we get out is the cumulative that we're looking for. So it's the same format, the COMTRAP-Z command, and then the time we're interested at, and then the quantity. It gives us the cumulative of that quantity over that time. So once we convert the flow rates to their cumulative versions, we can plug them back here and get the cumulative versions of XCH4, SH2, and SCO. Okay, so how we're going to find the delta? So here it comes. We said before that with the right amount of oxygen, we get those desired products. However, this is not always the case. With maybe less oxygen or more oxygen, we can get H2O and CO2 besides the products, and we need to know how to deal with it. So in order to calculate delta, we need to find some number of moles of oxygen versus number of moles of stereoxide, because in the end, delta represents the amount of oxygen lost relative to the stereoxide. So we start by saying, okay, how many oxygen is involved in this? So here, in this reaction, we're going to consider the reduction only. So there's no oxygen here, there's no oxygen here. Here, for every carbon monoxide molecule, there's one oxygen atom. Here, for every water molecule, there's an oxygen atom. Here, for every molecule of carbon dioxide, there's 2 atoms of oxygen. So this means that RO is the rate of water plus 2 times the rate of carbon dioxide plus the rate of carbon monoxide. And of course, the units are in milliliters per minute grams, because it's a flow rate, and this is the casual unit that we use. So once we have the flow rate of oxygen atoms inside the reaction, we can go ahead and convert it to some sort of moles per moles of the desired units. So since we're dealing with gases here, we can use the ideal gas law, and we can find this quantity, volume over moles, which is going to be RT over P, and this is going to be in units of liter per mole. We're going to be fixing those because actually we're trying to control those while the reaction is running, so we can use those directly, plug them here, and we get a quantity in units of liter per mole. Now we can go ahead and substitute that here, and with some unit conversions, we can see here we're getting rid of the minutes, dividing it by 60, and we take the inverse of that, multiply that by 1000 to get it to moles per milliliters, so that the milliliters can cancel out, and then finally we multiply that by the molar mass of the stereoxide, which is 172.115 grams per mole, and finally collecting all the units that are left over, we get moles of oxygen per moles of stereoxide times seconds, which is what we're looking for. And again, the formula is simple. This is the instantaneous. If we want to find the total or the cumulative, we just use COMTRAP-Z, the time that we're interested at, the quantity that we're trying to total, and we get that cumulative quantity, delta. So now everything is ready. We're just ready to plot XCH4, SH2, and SCO versus that delta that we just found. So here's it. It's shown in figure 3. We see that as the delta increases, this means that as more oxygen is getting lost from the stereoxide, more and more hydrogen and carbon, monoxide is produced. And with the increase in delta, the methane is just fairly constant if you were looking at the cumulative conversion rate of methane.